me to this workshop so I could talk about this work with you. This is, no, seriously, I'll be talking about a joint paper with Shui Chen, who's at George Mason, and Anindya at UPenn. So if you take one sentence away from this talk, the one sentence which kind of encapsulates the whole thing is that it's a talk about a problem at the intersection of sparse recovery and property testing. Just the setup, I think, at least for me, takes a little bit of mental space to kind of get it in my head properly. So I'll have a gentle sort of ramp up to the main substance of the talk by starting by reminding ourselves about, what are the basics of sparse recovery? How does it mesh with the property testing setting? Because even I think the statement of the result is a little bit involved. Maybe will require 2 looks for us. So, okay, I want to start with a little bit of basic stuff about sparse recovery, and we'll go through this by sort of considering a very simple and idealized example problem. So that'll be a problem of solving a system of random linear equations. So what do we mean by this? We have some unknown solution vector, just a vector of n real numbers, w1 through wn. And we're going to be interested in solving random linear equations to which this is the solution. So our first equation maybe is this thing up top. This linear combination gives us 7. The next linear combination of the wi's gives us 11, so on and so forth. So what do I mean by random here? Well, for now, just to keep things very concrete, let's consider a really simple, clean model of what these random equations are, how they're formed, which is just that every coefficient is independently +1 or -1. Okay, so we see all these positive W1, minus W2, minus W3, plus W4. They're all just formed by tossing coins to come up with the coefficient structure for the equations. So we can think about a system of random linear equations like this as, of course, a data set consisting of labeled examples. So we have these n-bit strings x, and we have the value w.x as the label. And our assumption that we have these random linear equations where all the coefficients are +/-1s just says that the distribution over the x's, if we want to think about it from this perspective, is uniform over the Boolean hypercube, -1, 1 to the n. Okay, so suppose we want to solve a system of linear equations like this. This is, of course, something we all know how to do. If we get n or maybe a little bit more than n equations, as long as we get n linearly independent equations, we can recover the solution efficiently. And this is, of course, just Gaussian elimination. So we're all very familiar with this. This is a simple problem. Okay, now I want to impose a little bit of additional structure in the assumptions. Let's think about solving a system of random linear equations where I actually know that the solution is sparse, okay? So it's not an arbitrary solution vector W in Rn anymore that we're thinking about. Instead, I promise you, we know that the solution has only k non-zero entries, okay? So the solution we're looking for is a very sparse vector. Think of k as extremely small relative to the ambient dimension n. So our system still looks something like this. And it's well known, kind of a foundational result in this area of compressive sensing is that if we have k log n equations, now we don't need n equations anymore because of this sparsity assumption. It turns out that with only k log n equations, we can recover the vector efficiently. And this is sort of a cornerstone result in this whole area of sparse recovery or compressed sensing. I'll talk a little bit more about this coming up. But before getting to kind of the good stuff, just sort of a throwaway observation. If we only care about sample complexity, this is actually a very easy problem to solve. You can imagine, well, if I know that the solution vector W is k sparse, there's only n to the k possible patterns, n to the k locations, n choose k places where those non-zero coefficients could be. So you could imagine just trying each one of them in turn. If I have a given sparsity pattern, I only need k equations in order to solve the system. And so I can just take my k equations, check if that is the right, solve, see if I get a solution which is then consistent with my other equations, and that'll basically tell me if I had the right sparsity pattern and got things correct. Okay, so this is not a very time-efficient way to do it. It's going to take us something like n to the k running time, but it's efficient in terms of sample complexity. So just a sort of quick, you can see with your own eyes, proof that the sample complexity of solving this problem is very low. It's going to be an easy problem to solve. So, okay, you don't have to be, Terry Tao or Immanuel Candes or Justin Romberg or David Donahoe to come up with that. The big contribution of this work that these guys did was that, of course, you can actually do this in a computationally efficient way. You only need polynomial time. You don't need n to the k time in order to do this sparse recovery. And this is by this L1 regression type algorithm. It's sort of the condition that we imposed earlier, this sort of very toy problem where we assume that the coefficients are uniform plus or minus 1 values, is unnecessarily restrictive. It's well known that if you have a weaker property, this restricted isometry property, that will be enough for this algorithm to actually succeed and efficiently be able to do this sparse recovery from just k log n equations. So again, this is sort of just the tip of the iceberg of a very large field, but it sort of sets the stage for what I want to be talking about in this context. Okay, so that's our whirlwind tour of sparse recovery kind of basics. Let's move on now and get to the other piece of the puzzle for us, which is property testing. So I think we all know what property testing is. We certainly will by the end of the week or by the end of the day today. The basic idea of property testing, we think about it, is that there's some massive object, some really, really big thing, maybe a distribution over an enormous domain, or a Boolean function with an exponential size domain, something like that. And we want to figure out whether or not the object has some property while making just a small number of local inspections. We only want to look at a very sublinear sort of portion of the object and figure out, solve this decision problem of whether or not it has some property. So just to remind us of kind of a touchstone problem in property testing that'll turn out to be related, at least in spirit, to what we're talking about, is this well-known problem of Junta testing for Boolean functions. So here we'll think of the sort of unknown massive object as being an n-variable Boolean function. Okay, so that's, you can think of it as a pretty enormous object of size 2 to the n. And the property we're interested in is this property of whether or not the function is a k-junta. So what does that mean? It means that the function really just depends on k out of the n input variables, right? It looks like f of x1 through xn, but in actuality, it's really just some function that depends on maybe 3 of the input variables, as in this example. And our standard way of thinking about property testing for Boolean functions is often that we consider a setting where we get to inspect the function via black box queries. So this is different than the sort of sample-based testing that Eric was talking about earlier. The usual way we would think about testing Boolean functions is that you have a membership oracle. You have a black box oracle, you feed in an input string, and you get back the value of the function on that input. Okay. So as probably most of us know, there are some notable successes in this area of Boolean function property testing. This was one of the early and very influential results by Fisher, Kindler, Ron, I think Safra, Semrenitsky, and there have been many refinements by Eric and other people over the years saying that, hey, we actually have, perhaps surprisingly, really efficient algorithms for this property testing problem, this problem of testing whether an n-variable function, Boolean function, is actually a k-junta or not. So we can solve this. If you give me any Boolean function, any n-variable function, there's an efficient algorithm which will say yes if the function is a k-junta. It will say no if the function is far from every k-junta, epsilon far from every k-junta. And you can do this with sort of this gold standard sample complexity. You make a number of queries to the, whoops, that should be queries to F, not queries to G, a number of queries which is completely independent of the ambient dimension of sort of the a priori size. There's no dependence on n. The number of queries required depends only on k and on the accuracy parameter epsilon. And that's really sort of the gold standard that's sometimes called constant query testability in property testing. That's what we really want. Okay, so we've seen a little bit of sparse recovery or compressive sensing. We've seen a little bit of property testing. What this work is about is combining these two strands. So we're going to be taking sort of a property testing look at a sparse recovery type problem. So what does that mean? How would you sort of formulate things? Let's go back to the sparse recovery setup and remind ourselves of how it works. Okay, well, it's about recovery. We're trying to actually figure out what is this unknown k-sparse vector from these linear equations or these labeled data points. And we saw this, famous result, k log n samples suffice. You only need k log n of these examples in order to do the recovery. Well, it's known, in fact, that for this recovery problem, the log n factor is inherent. This was shown by, I think, Kondo Ba, Piotr Indyk, a couple of other people. And for a range of different recovery problems of this sort, you really do need a dependence on n. There's no way to get rid of this log n in order to do the recovery. But that's exactly what we're sort of not happy with in the property testing context. Remember, the gold standard is constant sample, constant query testability. So this gives rise, I think, to a pretty natural question, which is, what if we relax our standards? We want to sort of stay in the sparse recovery framework where that's the kind of data that we're working with, but we want to only solve like a testing type problem. We want to solve the sort of approximate decision version of the sparse recovery problem. So here's how I think you could kind of naturally set things up. Let's say we are guaranteed that we're getting labeled data, which is labeled according to some linear form. So we get these examples x, w dot x. Again, we'll think of ourselves as just getting these uniform random x's, and we get these w dot x's corresponding to that. So we've got some unknown vector w. Say it has 2 norm 1, just for some normalization. And we want to figure out, is it k-sparse or not? So we're trying to solve like a testing for sparsity type question, given the kind of, access to the data that we would normally have in the recovery problem. So since it's a testing problem, we're again going to have these yes and no cases. In the yes case, it would be that the vector is k-sparse. There are only k non-zero coefficients. And in the no case, it would be that the vector is far from being k-sparse. And a natural sort of notion of being far from sparse that we'll work with is that you're far in 2 norm from every sparse vector. Again, since the vector w is a unit vector, it's natural to think about, is it the case that you have Euclidean distance, at least epsilon, from every k-sparse vector? So it's like a testing version of sparse recovery.
Sorry to interrupt you. Two very small questions. The the 2 norm of w being 1 is, unlike in the half space case, is not without loss of generality. So presumably you scale with that. And also, what if you're, what if there's a vector v that's like 2 k-sparse? Are you going to show a separation there, or?
Yeah, so we'll see the results will be quite strong. We'll actually distinguish k-sparse from from not k-sparse. We don't have to go to a relaxation where like you're far from being 2 k-sparse or anything like that. You're exactly right that there is like a built-in scaling here. We would define, in general, we define being far from the vector w just by like normalizing by the 2 norm of w. So when I say that like in this setting where the 2 norm of w is 1, our notion of being epsilon far from k-sparse is that for every k-sparse vector v, the Euclidean distance is 1. If I had a general vector w, which I wasn't assuming to have 2 norm 1, I would just divide. I'd have that the 2 norm of v minus w over the 2 norm of w is at least epsilon.
Right, got it. Thanks.
Sure, yeah.
Rocco, there are a couple of other questions. So Clement asks,
Great.
is the notion of k-sparsity in L0 crucial here? Could we have a sparsity in L1 or L2, either in completeness or soundness?
Great question. That's a lot to digest at once. Let's come back to that at the very end. But for now, this is the notion of sparsity that we're working with.
And Elias is asking, is the testing problem actually easier than the recovery problem?
Another great question, which is basically the main topic of the talk. So I'll address that in the next slide, I think. Yeah, so I think this is exactly, Elias nailed it. This is exactly the question that I think you would want to answer. And this, if you accept this kind of framework, a priori, it seems like the testing problem could be easier, right? Because we're not trying to do an actual recovery kind of thing where we have to, figure out where the relevant coordinates of W are and come up with these estimates. We just want to answer one, we just want to output one bit. Is it sparse or is it far from sparse?
So can I follow up on this question, Rocco, for a minute? Can you hear me?
Yes, I can. Nice to hear you.
Hi, how are you? So like the question I asked is like, if there is a sort of straightforward reduction that reduces the testing to the recovery. Because for example, in let's say distribution testing, right? Testing whether a distribution is monotone is harder than actually learning a distribution that you have the promise is monotone. So like root n versus something much smaller. So in this case, for these problems, can you like immediately reduce the testing to the recovery? Like, can you actually get a k log n upper bound?
Yeah, if you were to do the recovery, you could then look at your solution and you could say, oh, this is k-sparse or it's far from k-sparse or something like that. So I think the learning an algorithm for the learning problem, I think gives you a recovery type. Gives you a testing result. But we're interested in whether you can get testing results that would it could be achieved with a sample complexity which provably is not enough samples for learning.
Right. So is there a reason for that the sort of learning algorithms in this case are like in some sense robust, that if you're not sparse, you're like close to sparse, you get something to the closest sparse approximation?
Sorry, I don't understand the question. What is your question?
So yeah, I don't see this reduction, right? So like the learning algorithm like makes has an assumption that you are sparse and then you want to recover, right? The testing doesn't make an assumption, you don't have a promise. You want to test if you're sparse or not, right? Okay. So in principle, if the learning algorithm doesn't have any sort of guarantee, it's not immediately clear that you could use it to test. So Unless I'm missing something. So sorry to distract the
Yeah,
discussion.
let me not get derailed here. We can talk about it maybe offline. But the question we're going to be addressing now is whether we can solve the decision. Is the question that the main work is about clear to you? Whether we can solve the decision problem with fewer samples than the recovery problem?
The question is clear. I'm just trying to make the sort of a parallel to other sort of related questions where you do not have such implications. So the testing problem is not necessarily easier than the corresponding learning problem under the promise.
Okay. Okay. Well, to answer this question, it turns out that the answer is yes. There is constant sample testability in this framework. We don't have to have any dependence on n. So to give you a specific result for the sort of toy problem that I started off by talking about, where we're dealing with these uniform random, points from the Boolean hypercube as the x's, we give a result that problem can be solved by the, in this testing sense with a sample complexity, which is k over epsilon to the k. So it's worse as a function of k than the learning result or than the recovery result, but it has no dependence on n. Is kind of the big selling point. So this, I think, just says on the slide what I said in words, that if we compare this testing result with the sparse recovery result, we now have an exponential dependence on k, and that's an open question which we'd be interested in answering. What is the right dependence on k for this particular distribution? We don't know what that is, but we don't have any dependence on n, so we've sort of achieved this kind of gold standard of property testing. And one thing we can mention is it really is not the case that, oh, somehow we're sneaking around and doing like a learning version in order to get the testing result. If you think about learning, even to name a single coordinate out of the n coordinates, that's going to take you log n bits. And we're going to be using just a constant number of samples. So we're not getting that much information from our data. And again, I guess the last line is just driving in this point that the main sort of thing that we're aiming for and achieving here is independence of the ambient dimension. Okay, so this was a very special case that I told you about. I want to now describe some of the more general results, which are actually sort of the main substance of what we do. One generalization, the first one I'll explain, is that we can actually deal with noise in the data. So the noisy setting, let's say for now that the noise distribution is independent Gaussian noise. So this is actually going to turn out to not be very important. We'll see that we can handle almost any noise distribution, although we have to know the noise distribution. That'll come up later. But in this setting, for now, let's say we just still have independent x's drawn uniformly from the hypercube, but now we have noisy labels. So we don't just get w.x, we get w.x plus some Gaussian noise. In the recovery setting, it's known that the sparse recovery results will still go through in this kind of framework. And our results also go through in this kind of framework. So we can handle noise without really any problem at all, as we'll see when I kind of sketch some of the arguments. So let me just back away a little bit now. I want to tell you even more general versions of the main result, but before I do that, let me draw a little bit of a contrast with kind of the standard results in property testing that we maybe are a little bit more used to. So again, in kind of traditional property testing, at least of Boolean functions, what's going on? We usually assume we have some kind of query access. We usually assume we're dealing with a Boolean valued function. We usually don't consider the possibility of having noise in the data. So the differences I would want to highlight here are really along the lines of these 3 bullet points. We're dealing with real valued functions. So that's one kind of substantial difference from maybe Junta testing. We're making an assumption about the functions. We're assuming that we are dealing with a linear function. And within that class of functions, we just want to figure out whether it's sparse or far from sparse. Okay. Another difference, of course, is like we said, we're going to be able to deal with having noise in the data. And finally, a big difference is that, again, in most studies of property testing for Boolean functions, we assume that we get this kind of query access. Eric was sort of exploring, I think, a variant of the model, which is a very interesting one and deserves, I think, more attention than it's gotten, where you only have access to random samples. But that's a little bit unusual vis-a-vis sort of standard Boolean function property testing results. But the spirit of what we're trying to achieve is really very closely in line with sort of standard property testing. We're interested in getting constant sample testability. We don't want to have a dependence on n. Okay, so this is just a slide you've seen before. It's just a restatement of the result in this special case that we've been talking about. I want to highlight the things that are in red because those are things that will be changing when we go to a more general problem formulation in the next slide. So this is just saying if I have noisy data now, let's say that the noise comes from a normal distribution Again, my sort of distribution over the x's, over the random samples I get, is uniform over the hypercube. So this is just a restatement of the result we said earlier. We can have this efficient testing algorithm. It makes it needs a number of samples which is independent of n. It's basically k over epsilon to the k. And it'll successfully solve this testing problem. If the function is k-sparse, if the vector is k-sparse, it'll say yes. If it's far from k-sparse, it'll say no. So now we'll generalize this in a couple of ways. And the generalizations are again highlighted in red for you. So we'll be handling basically any noise distribution, as long as the noise distribution has moments of all orders, which even that is a little bit of a stronger condition than we actually require. We can handle any kind of noise distribution, although we'll have to know the distribution of the noise. And we'll come back to seeing why that's the case in a minute. So that's one generalization. Another generalization is we're going to go from just the uniform distribution over the Boolean hypercube to a much more general setting of being able to handle arbitrary product distributions. So the underlying distribution over the x's, remember x is an n-dimensional vector, it's going to have to be an IID product distribution, but it could be basically any distribution with one asterisk, as long as each coordinate marginal of the distribution is non-Gaussian. So the underlying one-dimensional distribution can be pretty much anything. It needs to have moments of all orders. It can't be a Gaussian. Okay, so if you give me access to this data from an IID product distribution where each component, the underlying distribution over the reals is non-Gaussian, you give me access to this kind of noisy data with basically any type of noise model, then it turns out that we have the same testing result. So again, we can distinguish k-sparse vectors from far from k-sparse vectors, and the sample and time complexity won't have any dependence on the dimension. They'll just be, you can see there's a dependence on this underlying distribution D, sort of that core univariate distribution. That will come into the picture. There will be some dependence on what is the particular noise distribution, depends on K, depends on epsilon, but no dependence on the dimension N. Okay, so this is basically the most general version of the main result. I guess, strictly speaking, we can do something more general because we can actually do tolerant testing or distance estimation. We won't just tell you whether or not you're k-sparse or far from k-sparse. We'll output an accurate estimate of the distance to the nearest vector, the nearest k-sparse vector. But if you don't care about tolerant testing, you can ignore this and just think about this as being our general result. So sort of arbitrary product distributions, which are not Gaussian. If we know the noise, we can solve this testing problem with no dependence on the dimension n. Okay. So at this point, you might be thinking these are slightly weird results. It seems like you have these various asterisks. You can't handle a Gaussian distribution. You sort of need to know this noise distribution and so on and so forth. So we also have a range of lower bounds which show that if I take away any of those conditions, then actually you can't get this kind of qualitatively matching result where there's where the sample complexity is independent of the dimension. So I'll tell you in the next 3 slides about 3 lower bounds, which say that basically if you take away any of these conditions, then the sample complexity of the testing problem becomes as hard as the learning problem. It'll go all the way back up to log n. So I'll tell you about these lower bounds. The first one basically is this Gaussian condition. It says you're not going to be able to solve this problem with a sample complexity independent of n if the distribution is Gaussian. And this is true even if you're just considering the simplest case of one sparsity. As a comment in this vein, this is why we sort of inherently have to have a dependence, if I go back a couple of slides, on the underlying ambient distribution D0. That's why there's this sort of O sub D0 in the sample complexity, because it should be easy to imagine if my distribution were very, very close to a Gaussian, well, it would be sort of getting harder and harder to solve this problem the closer it is to a Gaussian. And you can work out rigorous statements along those lines, which we do. But anyway, yeah, this first lower bound says, that this restriction in our positive result, that the distribution can't be Gaussian, is real. There is no efficient algorithm if the underlying distribution is Gaussian. The second lower bound result says it's really not enough to have a product distribution. You need an IID product distribution if you want, again, this constant sample complexity. So if it's not IID, if the distribution is allowed to even just have 2 different possibilities for what each sort of coordinate-wise marginal is, say Poisson 1 or it could be Poisson 2, then again, it's provably impossible to have a constant sample complexity. You'll need to have sample complexity, which is as bad as in the recovery case. It's going to have to grow like log n. So this IID assumption for the product distributions is really necessary. And the third assumption is that you really do need to, as we kind of stipulated, know the noise distribution. I can give you an example of a simple product distribution where if you don't know what the noise is, it could be one of two possibilities. It's either Poisson 1 or Poisson 2, and you don't know which one it is. Then again, this kind of logarithmic NM lower bound kicks in. So in order to get the sort of constant sample testability, which is our main goal, you really do need all these conditions that are in our main theorem statement. So I don't want to really say much more about the lower bounds. In the rest of the talk, I was going to give you some of the ideas of the upper bounds. For the upper bounds, there are essentially two different algorithms. There's a simpler algorithm for kind of the clean case that I started off with, where we just have the underlying distribution is uniform over the hypercube. And then there's a somewhat more complicated algorithm for the more general case of like an arbitrary distribution. So yeah, I'll try to say a little bit about each of those settings, but maybe just to motivate sort of the upcoming discussion, the natural questions which come to mind at this point are, okay, there's a positive result as long as the underlying distribution is not Gaussian. Like, why is that the case? How does it sort of emerge that you can handle non-Gaussian distributions, but you can't handle Gaussian distributions? Okay, we also will try to figure out, what is the dependence on the distribution, the noise, these types of things. So to get us going on actually understanding some of the results, really the key notion that underlies all of our positive results is the idea of working with the cumulants of the underlying univariate distribution. So let's remind ourselves of just the very basics here. If we have
Rocco, sorry, Joe has a question.
Oh, yeah.
Do we know that the first coordinate in the second lower bound, do we know that the first set of coordinates are Poisson 1 and the second set of coordinates are Poisson 2, or are they mixed up in a manner which we do not know?
I believe, if I remember correctly, even if you know that the first one is 1 and the second one is 2, it's that doesn't help you, because you basically don't, the sparsity pattern, if it's k-sparse versus non-k-sparse, you don't know how that would be mixed up in the one way or the other. So you can assume that you know that. Okay. Oh no, I see the question.
So quick question. Is this problem at all related to these problems on non-Gaussian component analysis, where you have access to some samples and it can be decomposed into some, from some ambient space, and it can be decomposed into some product of like a non-Gaussian Gaussian component, and there are some algorithms that depend on like exactly, how much you differ from the moment of a Gaussian in a particular direction?
Interesting. I don't know of connections there, but I don't know this line of work well, so there might be connections.
Adam, so very briefly, this is also going to use some notion about cumulants, and I guess those also use some notion of cumulants.
Right.
So, there's technical similarity. It's not, there's some technical similarity, certainly. Like, the fact that the cumulant of a Gaussian is very characterizing of the distribution is going to be central here as well.
Okay.
Yeah, this is previewing the next couple of slides. So, okay. Yeah, so let's remind ourselves of the basics of cumulants. What are the cumulants of a distribution? Well, we know what the moments of a distribution are, right? If we want to think about the moments, we can, recall this moment generating function, which is sort of a way of encoding all the moments of a distribution, just by having them be the coefficients of a Taylor expansion for the generating function. So the cumulants you can define as just, you take the moment generating function, take its log, and now look at the coefficients in the Taylor expansion of that function. And those coefficients correspond to the cumulants of the underlying distribution. Okay, so I guess strictly speaking, the jth cumulant is what you get if you take the cumulant generating function, you just break it down in terms of doing the Taylor expansion, and it sort of corresponds to exactly like the role of the moments in the moment generating function, but you're starting with log of the moment generating function instead of the original moment generating function. Okay, so given this notion of cumulants, even at the sort of very high level at which I just described it, it's probably clear that if I give you the cumulants of a distribution, you can get the moments back and vice versa. And indeed, they're really, really nicely related for the first couple of cumulants. The first cumulant is the mean, the second cumulant is the variance, and then it starts to get uglier. The third cumulant doesn't have such a nice expression or a nice way to describe it, so on and so forth. But you can see if I gave you the cumulants, if I give you the moments, you can obviously write down the cumulants. There are just, expressions for this, and you can go the other direction as well. So sort of knowing one is as good as knowing the other. However, that doesn't mean that working with one is always sort of as convenient as working with the other one. And it turns out that for our purposes, cumulants have some really nice properties which make things go through in a clean way. the key properties, and we'll see this is really almost everything we need, are really just two basic properties. The first one is linearity. If you have two independent random variables, then unlike moments, the sum of the jth cumulant of the sum is the sum of the jth cumulants. So they decompose, independent random variables decompose in a very nice way for cumulants here for every j. And similarly, they have this nice homogeneity property, right? If you scale a random variable by c, it scales the cumulant in sort of the obvious way. So this is going to turn out to be absolutely really, really convenient for us to have these properties. A couple of other facts about cumulants, which we'll end up using, are that the cumulants of just, this very simple Rademacher distribution, +1 - 1 with equal probabilities 1/2, we can write down what those cumulants are. It's just a little exercise to figure out that basically they're 0 if j is odd, and they grow as j to the j if j is even. On the other hand, for Gaussians, the cumulants have this very interesting property that, again, the first cumulant is the mean, the second cumulant is the variance, but then for any Gaussian random variable, all of the subsequent cumulants turn out to be 0. So cumulants 3, 4, up through infinity, they're all 0 for Gaussians, and this will be important for us. Okay, so at this point, we know enough to go through a sketch of the simple special case that we started off the talk with, where we think about the underlying distribution as being just uniform +1 - 1 to the n, that's where the x's come from. So in the next few slides, I'll sketch for you how in that setting, given let's say, data where we have Gaussian noise, although again, we'll see that the noise doesn't really matter, we'll be able to come up with this constant sample testing algorithm to distinguish between k-sparse, linear forms versus far from k-sparse linear forms. Okay, so how does it work? Really, it leverages the linearity and homogeneity. That's almost all it does. So just to remind ourselves of the basic setup, we get these samples. So we get the n-bit string x, and then we get w.x plus the noise. Okay, and remember, each of the coordinates of x is just this Bernoulli +1 - 1 equally likely random variable. And we're going to assume for now that the noise is Gaussian. So, okay, I get these samples of this, w.x plus noise. I can certainly draw a bunch of these samples and estimate the cumulants. For any j that I'm interested in, I can come up with a high accuracy estimate of the jth cumulant of that random variable y, which is just my stand-in for w.x plus the noise. And now, given the nature of the way the data is structured, I can just use these linearity and homogeneity properties to say, well, I have w.x plus independent noise. So the linearity lets me split those two pieces apart. And then w.x, well, I can just use the homogeneity property to say that the jth cumulant of that part is just going to be this sum of wi to the j times the jth cumulant of the Bernoulli. Okay, so this is just the part in red. The key part is just an immediate consequence of these basic properties of cumulants. So what does that mean? It means that basically I can figure out, or I can come up with some kind of estimate of this jth sort of power sum symmetric polynomial. So this is, the jth polynomial would be like the sum of w1 to the j plus w2 to the j plus so on and so forth. I just solved this simple equation in red, and I have that this jth power symmetric polynomial has this expression in terms of the jth cumulant of the labels that I get, the label distribution, the jth cumulant of the noise, and the jth cumulant of the Bernoulli distribution. So now you can imagine you're in pretty good shape. This is just the same thing as on the last slide. I can really come up with estimates, or in some cases, I actually exactly know these quantities on the right-hand side. I have access to these labeled examples, these draws from the y distribution. For the Gaussian, if I assume that my noise is Gaussian, well, then actually these jth cumulants of the noise distribution are 0. So there's nothing to do there. But even if I didn't have Gaussian noise, as long as I knew the noise distribution, I could just compute these jth cumulants of the noise distribution. And finally, again, it's some kind of exercise to write down and figure out what are the jth cumulants of the Bernoulli distribution. So we can figure out a good estimate of everything on the right-hand side. We can, in other words, we can come up with a high accuracy estimate of this jth power sum polynomial in these coefficients that we're interested in, w1 through wn. Okay, yeah, so this is just saying the same thing. I can figure out what's on the right-hand side, or I can come up with a high accuracy estimate. So I can work out for any j that I'm interested in, what is the sum of the squares of these coefficients? What's the sum of the fourth powers? What's the sum of the sixth powers? So on and so forth. It's convenient to work just with the even powers. I think I see a question from Clement. Does the lower bound on Gaussian D still apply if A is not Gaussian itself? That's a good question. Let me come back to it at the end of the talk. Yeah, I'll come back to that at the very end. Okay, but continuing here, we see that hopefully it's clear from this, even this high level sketch, that we can actually come up with high accuracy estimates of these power sum polynomials. So, okay, it's nice to have these estimates of the power sum polynomials, but if we're interested in figuring out whether or not our underlying weight vector is k-sparse, we might want to have some other kind of information about the vector. And it turns out that these other elementary symmetric polynomials, just the sort of more standard elementary symmetric polynomials, turn out to be more convenient for doing that kind of analysis. So I think I've written down here just a basic expression for what is the jth elementary symmetric polynomial. It's just the sum overall, I guess, n choose j multilinear monomials corresponding to picking every possible subset of the j variables and adding them up. I'm working with the squared weights here again because it's more convenient for what we're doing. So we have these well-known identities which say if I give you the first j elementary symmetric polynomials, you can figure out what the jth power sum polynomial is, and it goes in the other direction as well. If I give you the first j power sum polynomials, you can figure out the jth elementary symmetric polynomial. Okay, so we can again kind of go back and forth between these two things. And again, just reminding ourselves from a few slides back, we can estimate these power sum polynomials with just k to the k samples. And this is again because the sort of sample complexity, if we go back, really came from the denominator here. The fact that the jth cumulant for the +1 - 1 distribution was like j to the j. So that's where that sample complexity is coming from. So good, we can estimate these power sum symmetric polynomials. That means in turn, we can estimate the elementary symmetric polynomials. And now having a good handle on the elementary symmetric polynomials really tells us what we want to know in terms of whether or not the underlying vector is k-sparse. So these are just very basic observations. Suppose you have a k-sparse vector, okay? Then if I look at the j plus first elementary symmetric polynomial, it's going to be 0 because every monomial I'm multiplying together k plus 1 thing. So I'm always multiplying in a 0 into every sum end in the k plus first elementary symmetric polynomial. Okay, so that first observation is super easy. And the second observation, the converse, is equally easy, right? If I have that the k plus first elementary symmetric polynomial in these squared weights, which are always non-negative, is 0, well then actually each of those sum ends must have been 0. It has to be the k, which means that the vector has to be k-sparse. If there was even a single monomial of k plus 1 with non-zero elements multiplying together, I wouldn't be getting 0 out for the k plus first elementary symmetric polynomial. So you can see probably this converse is going exactly in the kind of direction that we want. In our testing scenario, we actually need a robust version of the converse, but that's not very difficult to come up with, right? So the converse said, I guess, that if W is not k-sparse, then the k plus first elementary symmetric polynomial is non-zero. And you can robustify this. It's pretty simple. I think it's an inductive argument that if your weight vector W is far from k-sparse, then in fact, the k plus first elementary symmetric polynomial has to not just be non-zero, but you can give a lower bound on its magnitude. Okay, so given this robust version of the converse, it's probably pretty clear how you would put these pieces together to actually come up with a testing algorithm. Again, the algorithm gets access to these labeled examples. It doesn't actually use the individual bits of x, though. It really just uses statistical estimates of the labels, this w dot x plus noise, this y part. And again, how does it work? It estimates these cumulants. Given estimates of the cumulants, we were able to figure out estimates of these these power sum symmetric polynomials. So the sum of the squares, some of the fourth powers, some of the sixth powers, so on and so forth. Given estimates of those power sum symmetric polynomials, we can estimate the elementary symmetric polynomials. And then we just saw that if the vector was k-sparse, this k plus first elementary symmetric polynomial will be 0. Whereas if the vector was far from k-sparse, then this k plus first elementary symmetric polynomial will be bounded away from 0. So we can successfully come up with the right answer in each of these cases, whether the vector is k-sparse or far from k-sparse. So that's a sketch of the simple result, the result in the case where the underlying distribution was uniform over the Boolean hypercube. Are there any questions about that result? Okay, If not, then I'll move on. So we saw that really the crucial thing for that result was that we were able to estimate these these power sum polynomials. And how are we able to estimate these power sum polynomials? Well, again, it just came from this very simple identity, which is a direct result of the linearity and homogeneity of cumulants. We have this division. When we solve for the power sum polynomial, we have the cumulant of the underlying univariate distribution, which in our case was just this Bernoulli 1/2 on the right-hand side. So this worked out well for us because the +1 -1 uniform distribution has these non-zero cumulants. So what we wrote down makes sense, right? This is a quantity that we could hope to estimate. The noise didn't really matter. Again, that was just this, minus the jth cumulant of the noise on top. As long as I know what the noise is, I can handle that no problem. But it's more interesting, it's more challenging what's going on in the denominator. When we were dealing with these uniform +1 -1 bits, okay, we know what those cumulants are and we can proceed. How are we going to handle a more general case? You can see already probably that if those cumulants are 0, we're going to be in trouble. And that's indeed what happens. So let me remind you now, and I guess most of the rest of the talk, I'll give you some sense of the argument behind the general theorem. So the general theorem we're trying to generalize, again, the sort of issue of the noise is not so important or not so tough to handle, but we want to think now about, okay, I no longer have +1 -1 as my distribution over each coordinate. Instead, I have a general distribution over the reals. And as we saw, the result is going to require that the distribution is non-Gaussian. So we'd like to figure out now, how can we solve this more general problem? Well, the natural thing to do is try to do just what we did before, right? Just instead of having the Bernoulli distribution, instead of having this Bernoulli +or -1 distribution as the underlying distribution, we just have this ambient distribution d0. Again, we can express these power sum polynomials in terms of the jth cumulant of the labels, these y's, which we can estimate from our samples, the jth cumulant of the noise, the other term in the numerator, which we can handle. And now in the denominator, though, we have this jth cumulant of the underlying distribution. And this could be 0 conceivably, right? Maybe it's the case that for one of these cumulants, which we would like to carry out this estimate and come up with the jth power sum polynomial, it doesn't make any sense because we're dividing by 0. In fact, maybe something even worse happens where we actually end up always dividing by 0 for every even value of j that we'd be wanting to be using in our algorithm. So these would be problems, and you can probably see the connection with the Gaussian challenge that arises now. For, I guess, the second cumulant, when j is 2, nothing bad can really happen, right? We know that the second cumulant is just the variance, so as long as I have a non-trivial distribution, I'll never be dividing by 0 because of j = 2. But we saw that if the underlying distribution is Gaussian, then that's where sort of, the good news ends. All the higher cumulants are 0, and so the algorithm really just can't work, right? There's not going to be any larger value of j for which it's possible to carry this out. But crucially, it turns out that having a Gaussian distribution is kind of the only distribution which can completely scuttle this attempt. The reason for this is this classical theorem due to Marcinkiewicz, which says that if you come to me with any distribution which is not a Gaussian, any distribution which has some non-trivial difference from a Gaussian, then in fact it's going to have not just some non-zero cumulants after j = 2, it's going to have infinitely many non-zero cumulants. So this kind of tells us, oh, there should be like a lot of tools at our disposal that hopefully we can use, these non-zero cumulants of higher order in order to make something like our approach work. And indeed that is the case, but it's not, we can't use the same simple algorithm based just on these symmetric polynomials that we used in the earlier case. So let's consider now the setting in which, the distribution is not a Gaussian. And again, parenthetically, we know from the lower bound that there's no hope when it is a Gaussian, right? There's no way we're going to be able to make it work. So we fixate now on the case in which the underlying distribution is non-Gaussian. Okay, we know we have infinitely many non-zero cumulants, but just because I have infinitely many non-zero cumulants, that certainly doesn't mean that cumulants 2, 4, 6, 8, 10, 12, the ones which we needed in order to reconstruct the elementary symmetric polynomials, will be non-zero. It's easy to come up with examples where the fourth cumulant is 0 or the sixth cumulant is 0. And in that case, we can't make our simple algorithm work. So we need to come up with a somewhat new algorithm. The idea underlying it is very simple. It's just that, if I go to higher and higher norms of a vector, those basically start to look like the infinity norm. And if you can figure out the infinity norm of a vector, well, maybe I can get rid of, maybe I can sort of take away elements of the vector piece by piece by piece. And that's exactly what our algorithm does. It turns out to be this iterative kind of thing where we estimate the largest magnitude entry of the vector, we compensate for it, basically subtract it away, then we estimate the next largest magnitude entry of the vector, subtract it away, and do something iterative like this. So I'll take you through a high-level sketch of some of it, but I won't go into too many details. This is just a basic lemma, which says something we're all comfortable with, I think, just that if I have a vector, let's say the 2 norm is at most 1, I'm willing to look at a large enough norm of the vector, the t norm for t something like 1 over delta cubed, then that'll be delta close to the infinity norm of the vector. Okay, so in principle, I'd like to figure out, exactly what is the magnitude of the largest component of this vector. I won't be able to do that exactly, but if I'm able to estimate a large enough norm of the vector, that should be morally just as good as getting the exact infinity norm of the vector. So, okay, what's the high-level idea of the algorithm? Basically, it needs a sequence of we'll see, these values can have to be very fast-growing, but a sequence of different sort of indices such that all of those cumulants are non-zero. Okay, so I want, the A1th cumulant is non-zero. That's a very large value, and somewhat lower than that, I have that the A2th cumulant of the distribution is non-zero. And smaller than that, so on and so forth, something like this. So I have these non-zero cumulants, k or k plus 1 of them, I think, is going to be good enough for me. Okay, let's consider, say, this largest value, this A1 value. We saw earlier, right, since this A1th cumulant is non-zero, just in the simple expression, I have a non-zero denominator, I can actually estimate this A1th elementary power sum polynomial. Good, so I have some kind of estimate of the sum of the A1th powers of this weight vector. Okay, since A1 was chosen to be very, very large, this is a high accuracy estimate of the largest magnitude entry in the weight vector. So I basically know the biggest value in the vector, the largest magnitude value in the vector. And, I'd like to now somehow strip it away and recurse. So this is just for the purpose of sort of, having clean notation. Let's assume that the entries of the vector are ordered from largest to smallest magnitude as we go through the elements of the vector. Since I basically know what is this largest value, I can subtract it out when I do my estimates of the other power sum polynomials. And that means that really I can sort of, do what I just did, but working with sort of this simplified version of the vector where I've taken away that largest magnitude element. Okay. So you just, you can compensate. I know what this largest magnitude value was. I figure out some power sum polynomial in these things. I can subtract away the appropriate power of that largest value. And now it's like I'm working with the sort of truncated vector where I've gotten rid of that large value. So you can imagine how something like this would go, right? You start with this very, very large norm. You get an estimate using that of the largest magnitude entry of the vector. Then you go down to some somewhat smaller norm. You, again, sort of recursively do the same kind of thing we just did to figure out an estimate of the next largest element of the vector, and so on and so forth. You do this k times. You'll actually come up with high accuracy estimates of the k largest elements of this weight vector. And once you've done that, you're pretty much home. So we've worked out now estimates of the k largest elements of the vector. And we want to know, well, is this vector k sparse or is it far from k sparse? I guess we're assuming that the true norm of the vector is 1, but even if we don't make that assumption, something we can always do with j equals 2 is just figure out the degree 2 power sum polynomial, the sum of the squares of the elements of this vector. So if I have these high accuracy estimates of the k largest elements of the vector, and I know the sum of the squares of all the elements of the vector, obviously that's exactly the information I need to tell whether the original vector is k sparse or whether it's in fact, has some non-negligible distance from k sparse. I think it should be clear also that this is enough information to let us do tolerant testing or distance estimation, right? We just see how much of the sum of the squares is left after we've taken out these k largest elements. Okay, good. So hopefully that made sense. But if we want to think a little bit more from like an effective algorithms perspective about how this would actually work, okay, what did we say we did? We said, okay, we're going to work with these k values, A1, A2, A3, these very large values such that I actually know that the cumulants of the underlying distribution, the A1th cumulant, A2th cumulant, so on and so forth, are all non-zero. Okay, so if I know the distribution, presumably I know I could in principle figure out these large values, and I know that the distribution has, you know, as many non-zero cumulants as I need. So that's good news. That means that this should be doable, at least in principle. But if you say to yourself, okay, how would this really play out in practice? It would be nice to know something about how far you have to go, right? This result of Marcinkiewicz says, okay, the distribution you started with, as long as it's not a Gaussian, I promise you that there are infinitely many non-zero cumulants. But a reasonable person could say, well, you know, given this particular distribution, can you tell me sort of where those non-zero cumulants are? Can you tell me, you know, you're telling me they're non-zero. Are they extremely close to zero? Because if they are, that's going to, you know, it's going to affect my algorithm's running time and so on. So these are, I think, natural questions to sort of try to bring this a little bit closer to an effective algorithm. So yeah, again, in order to run the algorithm, you need to know actually where are these non-zero cumulants, and maybe if we don't know exactly, you know, where these non-zero cumulants are, it would be nice at least to know how far do you have to go in order to reach the non-zero cumulants that you need. So the last result I'll tell you about is kind of a constructive version of this Marcinkiewicz theorem, which says, you know, under some mild conditions on the underlying distribution, we will tell you something about how far out you have to go. You know, do you have to go to the 100th cumulant? Do you have to go to the 10 to the 100th cumulant? How high up do you need to go to get a non-zero cumulant? And how large will that cumulant be? Okay, so this is, again, kind of like a constructive version of the Marcinkiewicz theorem. You need to assume something, right? Because again, if your distribution is, you know, closer and closer and closer to a Gaussian, well, it's going to be worse and worse and worse in terms of closer and closer and closer to really having only extremely small or all zero cumulants. So the theorem that we're able to give along these lines says, if you have a symmetric random variable, so symmetry is a straightforward thing. You can symmetrize just by subtracting two examples from each other. So suppose you have a symmetric random variable. Let's normalize to say the variance is 1. And the real meaningful assumption we make is that it has bounded support. It's supported between some minus c and c value. What we're able to say is that under those conditions, if you sort of have a starting point you're interested in, like, you know, the tth cumulant, the t plus first cumulant, t plus second cumulant, how far do I have to go to get a non-zero guy? The result says that if you start at the tth cumulant, you only have to go up to the basically exponential in tth. You know, consider that many possibilities for the cumulant, and you will find a non-zero guy within that range. So given any t, there's going to be some cumulant between the tth and 2c to the tth cumulant, which is not only non-zero, but it's actually bounded away from zero by this sort of doubly exponential function of t. So in principle, at least, this sort of tells you, you don't have to go you know, it's not the case that sort of I can't say anything about how far up you have to go in order to get k non-zero cumulants. But you can also see this is not going to give you a great result, right? I sort of have this tower of exponentials. To get the kth non-zero cumulant, I have to iterate this thing k times. So I end up with a tower of k, a tower of height k, but I can say that, you know, within that tower, I will have k non-zero cumulants, and that's sort of enough in order to run this algorithm. So we searched the literature a fair bit before kind of rolling up our sleeves, I should say, an India and Shrey rolling up their sleeves to actually prove this constructive Marcinkiewicz theorem. We weren't able to find results of this form in the literature. I think it's a natural question whether you can perhaps do substantially better. It may be the case that under different assumptions, or you can get a much stronger quantitative conclusion about how far up you have to go in order to get these non-zero cumulants. And that would be interesting. It would tell us something about the running time of the algorithm for distributions that satisfy these conditions. So I'm basically done. Just to wrap up in a last slide or two, we saw that the high-level message of what this talk is about is we're sort of looking at a sparse recovery type question from a property testing vantage point. We're interested in kind of the framework of sparse recovery, but we're lazy. We don't want to actually recover the unknown vector. We just want to figure out whether or not it's sparse versus far from sparse. And for a fairly general class of distributions, we can do this. We can, you know, sort of get a satisfying testing result with a sample complexity that's independent of the ambient dimension n. Although the testing complexity, it's a little bit reminiscent of like these graph property testing things where you have a tower type dependence in terms of the query complexity. So that seems to be where we stand. It's tolerant testing, like we said. It has this robustness property. So this is the last slide. I think a couple of interesting questions for future work are, it would be nice to have stronger quantitative statements, even in this very clean setting of, say, +1, -1 to the n, the uniform distribution. It's not at all clear that the result we have there, which was just this like k to the k query sample complexity, is correct. Maybe it's the case that you can solve that testing problem where the distribution is uniform over the hypercube with a polynomial and k dependent. So I think that would be interesting to think about. I think it's also interesting to think about going beyond just testing sort of sparse linear functions. You could ask analogous questions if you're interested in maybe low degree polynomials instead of linear functions, or some kind of passing it through some kind of function like a logistic function or something like that, or a sigmoid, to again extend sort of beyond just thinking about linear functions. And a last sort of broader question, which I think Eric has gone a long ways toward answering with the work he told us about earlier, is sort of in general trying to understand this relationship between testing and learning in a sample-based type of setting. So the next time I give this talk, I think thanks to Eric's work that he told us about, maybe I can put a check mark by this last open question. So I think that's it. Thank you.
Thank you, Rocco. I greatly enjoyed learning about the result. I'll Arnab had a question in the middle of the talk, but we kept it for the end. So does the test, so I'm repeating the question now. Does the testing question make sense for deterministic queries, but where the matrix of queries satisfies some pseudo-randomness condition like RIP or incoherence for recovery?
Yeah, that's a good question. I think you could formulate meaningful variants of the types of questions we're looking at along those lines. We haven't really thought about them at all. But yeah, I think that's a direction you could ask about.
Clement also had a question. Would anything be simpler if you had query access or active learning type access regarding sample complexity? Yeah.
Yeah, so a question a little bit in the other direction. I think the answer is yes. There are a range of techniques you can try to use if you have query access. I think it makes the problem considerably easier. I remember in the early stages of when we were working on this, I would keep on proposing to an India, oh, why don't we do this? And for like the 9th time in a row, he would have to say, Rocco, we don't get queries in this model. We just have the random example. So yeah, I think that queries do give you.
So with queries, you just have a junta, right? So you can probably do basically, I mean, it's a real valued function, but you can probably do junta testing.
You can do these kinds of things. Yeah. And again, it has this, we're assuming a lot of structure. It's, that it's linear. So it's, I think it seems to have a pretty different flavor. And I think it seems a lot easier if you get queries.
Do we have any other questions? Well, okay, there were lots of questions. Okay, so if not, then thank you, Rocco. So the next talk is by Dana, which is in 15 minutes. So let's take a 15-minute break and we will be back at 2:30 Eastern time, so 11:30 Pacific time. Thank you.